to another episode of NJ's Dojo. Today in the dojo, we will be tackling about energy and work. In our current era, we hear lots of terms revolving around energy and work. We may hear this from our parents who work tremendously hard and use energy as a component in order to be able to accomplish a certain task. In physics, these two terms inevitably correlate with one another. Work and energy are defined with correlational aspects in their definitions. Work is defined as the energy transferred to and from an object as a result of action of force. Whereas energy is conventionally described as the ability to do work. We will tackle energy in a much more complex definition later on, but for now, we know that energy and work correlates with one another. In this tutorial video, we will tackle energy. There are many forms of energy across the borders, but in this tutorial video, we will be tackling on mechanical energy. And this is subdivided into practically two types or two components of, which is kinetic energy and potential energy. Basically, these sub-concepts of mechanical energy has its own formulas. And to be able to understand it more briefly, we have to also know that the work formula is basically the force given to an object and it multiplied by the distance or displacement of the object, and that is the formula for work. Now we move on to the different components of energy. Basically, we know two different types of mechanical energy: kinetic energy and potential energy. In order to understand these two types of mechanical energy, kinetic energy is basically the energy drawn out from moving or force applied components. So for example, I have an object at a certain height, and due to the gravitational pull, it falls down to the ground. The moment in time wherein this certain mass is protruding towards the ground, it is actually experiencing kinetic energy, for the sole reason that force is being applied to it, and all the other kinematic and dynamic concepts are acting upon it. Whereas potential energy could be defined as energy that is stored. So if we go back to another diagram, we have a certain mass at a certain height, and the force of gravity acts upon it in order for it to fall, but it's still placed, let's say it's not yet released from the initial height when it's about to hit the ground. So basically, in this point in time when no force is being able to act upon it, or if all forces adding up to the object or mass is equal to 0, which means it's at stationary position, then that's when you can derive or assume that a certain object contains potential energy. In the physical side of things, we know that kinetic energy and potential energy are two different definitions of mechanical energy. Therefore, both of these energy contains different formulas. For example, kinetic energy is derived upon the formula K is equal to 1/2 times the mass of an object times its velocity squared. Whereas a potential energy has different types of subconcepts, may it be gravity or a spring. In this tutorial video, we will tackle the potential energy of gravity, which is mass of an object times times gravity multiplied by the height of where it's located. Okay, so let's try to get into an example of a problem that involves kinetic energy. So here we have this problem. A crystal vase with mass 2.40 kilograms is dropped from a height of 1.30 meters and falls to the floor. What is its kinetic energy just before impact, as we neglect air resistance? Okay, so in this problem, we realize that we need to draw the diagram first before we can understand or be able to evaluate the problem. So we know that a crystal vase, let's say it's here, a crystal vase is dropped at the height of 1.30 meters. And it drops to the ground at that height, and the mass of the object is 2.40 kilograms. Okay, so we know that the equation for the kinetic energy is K is equal to 1/2 mv squared. So basically we know what m is, but we do not know what velocity is. So in order to do this, we need to bring out one of the equations we used in the previous videos, which was v squared. This is a kinematic equation wherein v squared is equal to the initial velocity plus 2 times acceleration times distance. Okay, so here we know that the initial velocity of the crystal vase is basically 0, so we basically cancel that out. So we know that v squared is equal to 2 times AD. So now we have to plug in so basically we know that v squared is simply equivalent to 2 AD, and we can simply plug that in our kinetic energy equation. So we basically have 1/2 times mass times 2 AD. Okay, so now we basically have a working equation in order to figure out the kinetic energy. So we now plug in the variables. K is equal to 1/2 times 2.40 meters multiplied by 2 times, since we know that gravity is 9.8 meters per second squared, so we basically plug that in too, multiplied by the distance or the displacement of the certain object from the ground, which is 1.30 meters. Okay, and then we try to cancel out certain they're not variables, and multiply the remaining. So as we get our calculators, we know that the kinetic energy is 30.6. Basically, energy and work simply uses the measurement of J, or joules. And there you have it. The kinetic energy just before impact is 30.6 joules. Okay, so now that we've tackled kinetic energy and energy-related problems, let's try to answer a work-related problem. So here we have a German lifter, Ronnie Weller, won the silver medal at the Olympic Games in Sydney. He let himself lift 257.5 kilograms in the competition. Assuming he lifted the mass to a height of 1.83 meters and held it there, what was the work he did in the progress? So basically, we know that work is equal to the force times the displacement or distance of an object. So we know that so we can try to draw a diagram. Since the total force of an object includes the force given by the lifter upwards, and of course gravitational components as well. So basically, in order to know the complete force, we know that it acts upon the vertical axis. So we have to consider the weight of the object, and weight or basically the force of gravity is simply equal to mass times gravity. So basically, we simply have to plug that variable in our working equation for work. Okay, so finally, we have a working equation of work being equal to the mass of the object, or the weight, multiplied by gravity multiplied by the height. So basically, you have to plug in the equation. So we've got mass as 257.5 kilograms multiplied by gravity, which is 9.8 meters per second squared, and multiplied to the height, which is 1.83 meters. So basically, as we multiply it, we know that work inevitably becomes 4.62 kilojoules, since we're tackling with kilos. So basically, that's how much work the lifter did in order to lift the weights at a height of 1.83 meters. Okay, now that we've tackled on what work and energy is on the basic level, we have to understand another concept in the ideas of energy and work, and that is the conservation of mechanical energy. As we all know, energy is something that does not renew or does not loses its value over time. Basically, it could be just transferred into anything. Let's say mechanical energy can convert itself to electrical energy or heat, and the value of it remains at its utmost appearance. So we have to understand that energy is conserved all throughout the system, and that is known as the isolated system, wherein, for example, we have a diagram of a certain object located at a certain height, and it falls to the ground. Basically, when the mass is yet to be released, we know that potential energy is stored within the mass, and as it falls down, and for example, in this moment of time, potential energy simply becomes kinetic energy. And eventually, as it falls down, it renews and constructs the same potential energy it has back when it was held from the top of a certain height. And another example would be like a pendulum. For example, let me change color. For example, if a pendulum is swinging in these different positions, its first position is A, second is B, and third is C. At point A, we know that the object is at stationary position, meaning all the potential energy is stored within A. And as B occurs, we know that the object is moving and that kinetic energy is happening. And eventually, as it reaches C, it once again contains potential energy, for it remains at its most static point of the diagram. So basically, in order to understand this more, we need to know the definition of mechanical energy. And mechanical energy is defined as E equals the total kinetic energy plus the total potential energy. And as we all know, the total mechanical energy is conserved once the change in mechanical energy is simply equal to the change of kinetic energy plus the change in potential energy. And since energy is conserved, we all know that that equals 0. An alternative way of writing this is basically K plus U, kinetic energy plus potential energy, is simply equal to the initial K plus the initial U. This relationship is inevitably called the law of conservation of mechanical energy. But it does not imply that the kinetic energy of the system cannot change or that the potential energy alone remains constant. Rather, it states that their changes are exactly compensating one another and thus are offset to each other. Okay, now that we have an understanding of the conservation of mechanical energy, let's try to use it in a certain example. You are tasked to defend your tower by using a catapult which could lob a rock with a launch speed of 14.2 meters per second from the courtyard onto the attacker's camp at an elevation of 7.20 meters just below the courtyard. Okay. What is the speed with which the rock will hit the ground of the attacker's camp? Okay, so before we can solve this problem, we have to draw a diagram. So we know that a certain catapult is located at this point. And of course, since it's being lobbed towards the attacker's camp, and we know that catapults move in a projectile manner, so we can draw it like this. And since we know that the catapult is 7.20 meters above the ground, so we know that. So this will basically be in line with the attacker's ground. So which would mean we are looking for the point in time where the catapult will reach the ground, and it would be located right about here, 7.20 meters. Okay, so What we can do in this situation is realize that we can use the conservation of mechanical energy to solve this type of problem. So we know that total mechanical energy is E is equal to kinetic energy plus potential energy. And we know that kinetic energy is 1/2 times mass times velocity squared. And we know that potential energy is simply mass times gravity times the displacement or distance of the y-axis. Okay, so the first things we have to do is simply substitute these equations, k and u, to our working equation. So we have E is equal to 1/2 times mv squared plus mgy. So what we do know is that 1/2 mv squared plus mgy is also equal to 1/2 mv initial velocity plus mgy, the initial velocity, the initial displacement. So basically we try to cancel out, and we know that m gets cancelled out in all of the working variables, so we are left with 1/2 v squared plus gravity times y is equal to 1/2 v initial velocity squared plus gy. Okay, so now that we've got a working equation, we have to plug in variables. So we know that the initial velocity is 14.2 meters per second squared plus 2 times 9.8 meters per second squared and multiplied by the displacement, and we've got 7.20 meters. Okay, so as we try to calculate that, we would get an answer of 18.52 meters per second. And that is how you get the speed of which the rock will hit the ground using the idea of conservation of mechanical energy. Now that we've understood the ideas of mechanical energy, we also need to understand that energy can also build up. For example, if they usually say that a team is unstoppable when momentum is on their side, or when the energy that fills their bodies are at utmost achievable. In physics, these concepts can also be defined within the ideas of momentum and impulse. Momentum is basically defined as the product of an object's mass and its velocity. So basically, it's also known as linear momentum, which is defined in the variable p, which is equal to mass times velocity, as we all know that. Impulse, on the other hand, is the change of momentum, which would mean that the change of momentum is simply equal to the final momentum subtracted by the initial momentum. Inevitably, impulse is defined in the variable j, which is also equal to the average force multiplied by the change in time. So say for momentum is also conserved all throughout a system, and these usually occur in collisions. So for example, we have these three different types of collision that seeks to show how linear momentum is actually conserved, which would mean despite a collision in the system, energy is actually being transferred in each other, or basically it will form as one entire system. So to give you an example, I will mimic the collisions for each of these three classifications. So first we have elastic collision. Elastic collision is basically when two objects, for example, I have object A and object B. An elastic collision occurs when there is only a certain point of time wherein these two objects would collide, and basically they just simply bounce off from one another. So for example, we have two cars, two objects running towards each other, and when they collide, basically they just hit each other and move to its opposite direction. And that is elastic collision. And elastic collision is basically defined as mass of the first object times initial velocity of the first object plus the mass of the second object times its initial velocity, which is equal to the mass of the first object multiplied by the final velocity of the first object plus the mass of the second object times its final velocity. So basically, if you all notice, mv is actually momentum. So we have p initial 1 plus p initial 2 is simply equal to p final 1 plus p final 2. That's basically elastic collision. Now in elastic collision, it's a whole different type of collision, because basically elastic collision, they're still two separate objects, but in elastic collision they become a single system. So for example, I have this guy. Okay, he's staying put. He's running towards, let's just say he's standing still. An elastic collision occurs when the momentum of each object basically collides with one another and becomes one whole system. So for example, I have this object running towards the wrestler. So as it moves and collides with the wrestler, it becomes one moving object, compared to elastic collision wherein they bounce off to separate directions. An elastic collision occurs when the two objects basically stick to one another and become one moving object. And that is defined in the equation of the mass of the first object times its initial velocity plus the mass of the second object times its initial velocity is equal to mass 1, quantity of mass 1 plus mass 2 multiplied by only one final velocity, since they share the same velocity. And finally, another example would be explosion. Explosion is basically having both objects at rest, and for some reason a force pushes them away from each other. They're not colliding, a force just simply pushes them away from each other. This other as from the explanation itself, we know that it could be a bomb where it just explodes. Then we all know that particles fly out away from the center of explosion. It could also be as simple as two people pushing each other away. In this case, for example, if the engine of the car inevitably explodes, like boom, these two objects will move far away from each other. And that is defined as mass 1 times its velocity being equal to negative mass 2 times the second velocity. And basically, those are the types of collisions that would occur when you're trying to explain the conservation of linear momentum. So let's try an example. A collision is perfectly inelastic when object A runs into object B at a speed of 3 meters per second. Object B was originally motionless, and both A and B have the same mass. How fast are the objects moving after the collision? Okay, so this is perfectly inelastic because we know that one mass is motionless, and basically they have the same mass. So, as we try to draw this, we know that object A is running to motion B, to object B. And let's say, since mass is not given in this problem, to make a point, okay, since mass is not given in this problem, okay, let's figure that out later. But now that we have the diagram, A moving towards B at 3 meters per second. Okay, so since it's perfectly inelastic, we use the formula of inelastic collision, which is mass of the first mass times its initial velocity plus mass of the second times its initial velocity, which is equal to mass 1 plus mass 2, and you're looking for the final velocity. So since you're looking for the final velocity of both masses after the collision, you can simply derive the equation as Vf is equal to m1 v1 plus m2 vi2, don't forget the I there, over mass 1 plus mass 2. Okay, so since math is not okay, so since we know that object B is motionless, its initial velocity is inevitably equal to 0. So basically we can just cancel that out. We can cancel this equation out, leaving us with Vf is equal to mass 1 2 over mass 1 plus m2. Okay. So basically we need the mass of the object. So since it's the same mass, you can just simply substitute a certain variable. So let's say we can assume that the mass is equal to let's say 5 kilograms. So we have something to plug in. You can inevitably choose to not assume, but then for the sake of answering the problem, let's try to plug it in. So now that we have a mass, and since both masses are equal for both objects, we can simply plug it in as 5 kilograms times meters per second squared, no, not squared, sorry, over 5 kilograms plus 5 kilograms. So we know that our final velocity inevitably becomes 15 over 15 kilograms times meters per second over 10 kilograms. Cancel out kilograms. So we are now left with 3 over 2 meters per second. And that's how you solve for the final velocity. Note that this problem could be solved even if you do not assume a mass, since it's basically the same. As we continue this, we can simply rename mass 1 and mass 2 to simply mass because they're the same. So if I were to solve it In that way, we can have it as m times the second initial velocity over 2m, since we just simply add them. And we cancel out m, and we know that the initial velocity is 3, so we just plug it in. So 3 over 2 meters per second squared. And that shows the same answer. And that is an example of an inelastic collision. So there you have it. Today we were able to discuss about energy, work, the conservation of energy. We were able to talk about momentum, impulse, and the conservation of linear momentum, and we were able to solve different problems revolving around such concepts. Okay, so now I guess that's enough for today, and that's all we have for the dojo. So for now, the dojo is closed, and this has been NJ's Dojo signing off. See you in the next video.